Yeah, I would like to review quickly about the true positive. So in which case, what is the meaning of the true positive? Yi Jian.
Whether is abnormal and whether is classified as
No, positive.
true positive.
Positive is
Abnormal.
abnormal and well, yes, okay. True positive that is also classified as abnormal. Okay. False negative, 关轩.
False negative means normal, so you classify the false normal. That means you didn't detect the defect.
Okay, actually it is defective. However, it is mistakenly identified as normal. Right? And okay, false positive. False positive. Somebody. Keith.
Positive means abnormal.
Abnormal.
And we think it is normal.
It's a normal, however,
Yeah.
so it's like a false alarm, right? This is like this is Taiwan error. Right? And true negative, yeah, I mean the normal identifies as normal. This is normal wafer identified as a normal wafer. Right? So accuracy. So the denominator going to be the total number in the text size, in the text set, right? Numerator true positive, and true negative on the diagonal of the confusion matrix. And precision, what is the meaning of the denominator? True positive and false positive. True positive and false positive. All the number identified as normal. And within all the wafer identified as abnormal. Out of this, how much percentage are correctly identified as abnormal, right? The procedure. Like 100, you identify 100. Out of 100, how many wafers are correctly identified as abnormal? So we call the precision. Okay. So specificity. Specificity, true, negative, false positive. What is the meaning of the denominator? Inja. Specificity. What is the meaning of the denominator? True negative plus the false positive. In the test set, the number of the total normal wafer, right? In the normal wafer and the true negative. Out of all the identified normal wafer, what is the percentage correctly identified as a normal wafer? Specificity. And then sensitivity. Sensitivity. Yes. Sensitivity also known as a recall. Sensitivity. So F sensitivity is for all the true positive results. The true positive, false negative, that means there's a total number of the abnormal wafer. Out of the total number of the abnormal wafer, what is the percentage has been identified, has been screened out. Right. So what is the difference between sensitive and the precision? Sensitivity, precision. This is look alike. Yeah, precision and the sensitivity. This really look alike. What is the difference? See what I'm saying? Chen Yuan, what is different between what are the differences between prediction and sensitivity? Yeah, Jen, you can answer as well. Guangxuan or somebody?
I think the precision is focused on the negative result and
Negative?
the
No.
positive
Positive result,
and the statistic
It's
is
also on the positive result as well.
is one of the negative result and one of the
Positive
positive
result.
result.
Yes, a little bit different since precision. What do you think? What is the difference?
One is based on the result of
Classification result.
Another is
Based upon the true fact. Different, right? The denominator. This is based upon the classification results. Classification results, right? Based on classification of the result pertaining to the instance identified as positive, right? This is based upon the true fact that is pertaining to the abnormal wavelet as well. I'm sorry, in the sensitivity. I'm sorry. Okay. Then finally, F1 score. F1 score is a criteria for integrating precision or sensitivity. This is called a harmonic average. So F1, the integrating the precision and the sensitivity is like a balance. So if F1 score, the one that means there's the weight between precision and the sensitivity is a 1:1. So higher, it indicates the model is more robust, higher. So typically, if for me, in the collaborative industrial and academia project, we wish to meet the buyout criteria. Typically, we reach the F1 score at least a 0.95. 0.95. This is really high. Then the 14, yeah, very important one. Called the false part for negative rate. False negative proportion of the model classified falsely. For all the false negative results, the proportion of the model classified falsely. So it can be defined as follows. So look at that. False negative, true positive. So this is a total number of the abnormal, right? And the false negative, that means the portion has been unable to identify as a abnormal, right? So we wish the false negative rate as low as possible. No, yes, that's the false negative. So we wish to identify. So if this is reduced and sensitivity increases accordingly. If this is reduced and the sensitivity increases automatically. Alright, so yeah, this is an important message which I can just read along with you. The robustness of classified is demonstrated through its consistency, reliability across multiple evaluation matrices. While accuracy provides a general measure, however, do not blindly trust accuracy only. It often falls short in explaining performance imbalanced data set like this. So precision and specificity gauge the model's effectiveness in reducing false positive. Yeah, false positive. Yeah, try to so specificity the larger, so the lower false positive, and while sensitivity and the F1 score assess is a success and identify a true positive. True positive striking a balance between the precision and the recall. So and finally the false negative rate. False negative rate becomes especially critical when the missed positive the positive prediction carries significant consequences, like 1 out of 100, only one, the yield rate is 99. However, this batch has is a mistakenly identified negative, then they will ship to the customer. It causes a lot of consequential outcome, which is cause significant, we call the external quality cost. Like a batch of look at that. So wafer, very difficult. So okay, this is a wafer. Like this is 300 millimeter. This is die. Yeah. Now how many die? For example, I make it simple. The 300 millimeter, there's a 10 by 10 going to the 100. The 100 die, right? And a cassette. This is a cassette of the wafer. It's about 24 wafer, so by 25 wafer. So only this is a 2.5. So yeah. So that's why is the one cassette of the wafer is mistakenly released downstream to the production pipeline. The 2,500. The die going to release and should be recalled then. So it's going to affect the end product of the iPhone. Even though 1%, 1 out of 100 costs such as. So this is only a quite simplified version. So there's an additional consideration should be taken. Right. So I will experimentation of the road trace data augmentation. Yeah. So okay. So this is called the plasma enhance. The chemical vapor deposition process collected from the renowned fabrication in Tainan Science Park. Actually, the data is from UMC. Then, yeah, look at that. So this is two augmentation structure of augmentation. It can be generated abnormal or cyclic normal. So let me tell you something. In my application, the cyclic abnormal generation exhibit more stable augmentation outcome or result than the generated one. So this is start input normal the wafer data, and this start input the generate abnormal data. Then these two cycle can be utilized to evaluate the cyclic loss function. Then Yeah, look at that. The originally table 1, the classification results. You can look at the accuracy, 95%. Great. This is naive based Gaussian. 96 data boost. 95 the extreme gradient boost. 95 for the light boosting. Yeah, look at that, and then false positive, no type 1 error. How about this? False negative, 12, 11, 12, 12. Yeah, so tight. The number is not that, the number, purely number can be neglected, however, 12 batches. Like that, 12 batches. Can you imagine? The more iPhone will be recalled, right? So it can transform the ratio 38, 35, 38. This is so big. So sometimes we do not merely look at the number of the accuracy. Instead, we look at the accuracy position of the false positive, false negative rate. This is type 2 error, or called the consumer risk. See what I'm saying? So merely look at that. No, it's really misleading. So, any questions so far? Jen?
Yeah, I'm curious about why we, in the end, we use the generated abnormal data to train the model, or the cyclic normal data to train the model.
Can you say it again?
In the end, we feed our, in the end, we will use.
No, we train the entire model. Finally, we use the since finally the cyclic generates. So I will show you the result to explain why.
So in final, we use the cyclic.
Cyclic. Let me show you. Okay, this is an MSE. We compare MSE. So take the square of that. So that means the deviation, if the deviation increases and the square going to be penalized, getting larger, right? Exponentially, or MAE, the mean absolute error. So let's look at the comparison results. As Yi mentioned, look at that. Right? First of all, the table 2, evaluation augmentation strategy based upon MSA and MAE. First of all, we compare augmentation like a generated cyclic, yeah, 351 compared 91. And then, well, this is 3 compared to 30 compared to 4. Yeah, wow, this is no comparison. 1, 2, 1, 2, yes, that's what I did 4. And cyclic MAE, yeah, look at MAE, the 3,000, only 400. Yeah, this is a little, no, yeah, sometimes. So this is not overwhelming. So on the overall scale, so the cyclic perform better than the generated one. Why? Since we use a double transformation to make the training stabler. So cyclic provide a stabler generated result. This is the major reason. So that's how before I perform the research, I look at the structure before I predict the cyclic perform better than that. So it just proved my conjecture. So for SVID 4, you can see that 170 compared to 88 compared to 90, 28 4, 29 18. So it's quite evident, right? And then so this single SVID and this is single, like single SVID and the single So finally, look at that. Which one you like to choose? Cyclic, for sure. Then second question to be answered. Which strategy should be used? Single SVID or single wafer? Yeah, compared to the single. This is a single wafer. This is, wow, look at that. 18, 17, yeah. This is 128, 1129. Yeah, the single wafer. The single wafer perform better. Why? Since it portray or it investigate more deeper understanding of the nature from the SVID to SVID. Look at that. This is SVID. This is 800. This is only 200. So there's no comparison. No comparison. Okay, then by doing so, we also there's a quite famous one who would like to remind you called the smokes. Most of temporal data augmentation procedure. This is very famous back in 2002. This is attracted a lot of citation called smokes, synthetic minority oversampling technique. Let me show how it works. How it looks like smokes. Let me show you. Since in this paper in this paper, I only give a citation. I do not delve into the detail. I show you. Yeah, it's a very famous motivational oversampling. So yeah, here's a set of the data. A set of the data of diffracted wafer. We just pick one, like the small set of the minority class. The data of the minority class. We just take a randomly sample one. And also randomly sample the second one. We do the linear combination this plus the 0.3 of this to generate the other one, and put it back, sampling with replacement, and randomly pick one, and randomly pick the other one, and this plus the 0.3 of the other one. That's it. That's it. Yeah, look at the equation. Random oversampling. This is called the small. The other more straightforward called the bootstrapping. Bootstrap. Yeah, it's more naive. It won't matter. Yeah, close your eye every time you just pick one. That's it. And put it back and the sampling request and well, the keep sampling. It's stupid, right? However, sometimes it works. Sometimes it works. Called the bagging. Sometimes it's called the bagging or bootstrapping. This methodology can be dated back to the Leo Breiman, who was a professor in the Department of Statistics in, I believe, in Berkeley. That should be in Stanford. That should be in Stanford. Back in 2001. Yeah, let me see the question. What I see the question? No? Where's your question? Come on. Where's your question? No. Small. Do you have that? Send me. No, this is not. Like small weekly free dictionary. No. How come? There is the equation. Wicked. Yeah, let me show you some. Well, I need the equation. No matter is the Chinese or not. No. Where is it? Come on. No. Where is the equation? Medium, yeah, whatever that's Where's the equation? Come on, show me the equation. Still good. Micro analyze yeah. There we go. Yeah, original paper, 2002. There we go. Yeah, recall, precision, and so on and so forth. Small. Yeah, small. No. Undersampling. So. No, okay, look at the algorithm. You understand what I'm talking about? Yeah, the number of the minority, always focus on minority since the minority, this is the target group would like to generate. Among small, the percentage number of the nearest neighbor, or we just choose so in this we choose the nearest neighbor, K is the nearest neighbor, and we'll pick the nearest neighbor to generate. So it has no sense you just choose a farthest neighbor. No, it has no sense. And synthetic minority cross sample, how much percentage? Small d, this is a randomly t minority cross sample device. So, and choose smallest to be integral. So okay, so the p is. Yeah, let me see. Sample synthetic. This is compute the nearest neighbor populate function generate set. Okay, this loop is used to choose the neighbors. Then this is the second loop is used to indicate how the synthetic sample is generated. Choose a random sample among 1 and k, call n the step that choose one of them, the nearest one. So this is the target, this is the nearest one. Out of this one, you just randomly pick one and perform the linear combination. Yes. Yeah. Sample one, compute this, and this, minus this. Between one, there's a randomcy, the synthetic equal to the sample plus the gap, and the times the difference. So this is the difference. That means just we want to, so like this. We evaluate the distance, and this is target plus the portion of the distance to generate the third one. So all the generate will lie within the segment between these two. See what I'm saying? Yeah, I need to have a question. Oh no, I need to have an equation. Let me give you a minute, and I'll let you go. Or we look at that. We look at it. Yes, something like that. like this. You understand what I'm talking about? The new one, this is the target. For the W is a ratio. It's a random number between the so x minus x, this is a distance. So where W is a uniform random variable between 0 and 1, and x, so pick one of the k nearest neighbor belong to the minority process, so is also, if the k is equal to 10, use a k and n to select the 10 nearest neighbor, that's it. And create a pattern, the new sample on random sample, the segment connecting the pattern and select the neighbor. That's it. That's it. Yeah, that's it. So so this is original one, this is original one, then subtract on the segment on the portion. That's it. Yeah. Okay, as simple as can be. So I think time's up. I will stop here. So remaining, well, let me give me 5 minutes. I wrap up. I wrap up a little bit. So this is the simulation. So see, this is synthetic data profile 1 from the generated. Sometimes the local detail cannot be portrayed correctly by using generated abnormal strategy. However, look at that. That's quite. The general one, original one, the almost, yeah, the local. This is very refined. Really, well, the detail has been correctly identified or correctly portrayed. Finally, we would like to see that the false negative rate. Down to that, the 60%, 60%, boom. This, the F1 value has been raised up to the 0.96. So, yeah, single wafer, the only 45 wafer are required to be augmented. So this is, so it's not necessary to augment the same amount of wafer equivalent to the number of the normal wafers. And then, so, anything else? So, I need to wrap up, okay, I need to wrap up. And there's an additional, in addition to the algorithm, we also compare the different. The cycle gain I compared to the smokes. I also compared to the compare the cycle gain model to the bagging and the W gain. I mentioned last on Monday. DC did a convolutional gain and the style. I also compared to the diffusion model as well. So so this is a result. The cycle gain exhibit much better results. And this is some references. This some jihad and the synthesize the Roche's data and compare. So you can see that the cyclic in here now generated is not so good. And for SVID in here. Look at the discrepancy. And well, SVID right here, this is cyclic, the generator, yeah, something like that. And finally, yeah, there's a different, yeah, let me, hold on. Diffusion. Can you search the keyword diffusion? Tell me where the page number I mentioned diffusion. DIFFUSION.
That's true.
Page 12. Page 12?
Yeah.
Yeah, let me see that. Page 12.
Before the creative also should.
Oh no, there's another place. the earliest place in the article I mentioned diffusion. Did I? Oh really? Okay, maybe I mentioned in the response letter to the editor, not in the original paper. Actually, I did the diffusion. I did the diffusion model. However, it doesn't work that well. All right, and next week, please bring this. I will just recapitulate the remaining part for the GN. So I think this paper gives you an overview of the game's advantage. Yeah, this is a really nice example for you to get into the detail about the game, the generated adversarial network. All right, so VAE. So VAE homework AE homework will due 2 weeks from today. All right, see you next week. Thank you. 同学，你要记得把这个都搂上去。不是。
哦，有。
对，我就不会去检查了。